Dear students, today we will discuss about the uni-junction transistor. That is the semiconductor device and have the very important role in the semiconductor and device as a applications. So UJT uni-junction transistor, that is the pictorial picture view of the UJT. It have the three terminals. One is the emitter and second one is the base B1 and third one is the base B2. So uni-junction is the three terminal semiconductor device and use a oscillator relaxation device. So uni-junction transistor, here the basic construction of UJT. In this UJT there is a N-type layer semiconductor and second is the P-type semiconductor layers. So in this UJT, these two semiconductor materials are joined to each other, and after the join that form the a UJT unijunction transistor, which have the emitter terminal, base one terminal and base two terminal. So second figure show the symbol of the UJT and the last circuit diagram show the equivalent of circuit diagram of the unijunction transistor. So the UJT can be represented by a two resistance, that is across the base 1 RB1 and across the base 2 RB2 and a diode D. So two resistance and one diode form a circuit diagram of the equivalent UJT transistors. So equivalent circuit of the UJT, the equivalent circuit comprised of two resistors, one fixed RB2 and one variable RB1 and a single diode. Here is one resistance RB1 across the base B1 is variable resistance and the resistance RB2 is the fixed resistor, that is the across base B2 and a single diode D. Now RB1 varies with emitter current IE. So here emitter current depend on the base resistance RB1. This circuit show the equivalent circuit of the UJT. So here is the one diode, two resistance across the two base, and here the voltage across the base is the BBB, and voltage across the emitter and ground is BEE. So the current flow in emitter is the IE, and voltage across the diode is the VD, and also voltage across the RB1 or variable resistance is the eta BBB when emitter current is 0. And equivalent resistance across the two base B1 and B2 will be equal to RB1 plus RB2 when emitter current is 0. So this is the equivalent circuit diagram of the UJT. RBB is the interbase resistance when IE is 0 or RBB equal to RB1 plus RB2. So this is the sum of the two resistance. So typical range of the RBBB is 4 kilo ohm to 10 kilo ohm. So this is the typical range of the base resistance across the two base. The position of the aluminum rod determines the relative values of RB1 and RB2. So what is the voltage across the RB1, base resistance RB1? So we can find out this voltage with the help of voltage divider rules. So here BRB1 equal to RB1 upon RB1 plus RB2 into BBB or equal to eta BBB when ammeter current equal to 0. So here eta is the and equal to RB1 upon RB1 plus RB2 when ammeter current is 0. So this is the value of eta. This is also equivalent circuit of UJT, and now next one is the peak voltage in the UJT. So the peak voltage of UJT will be eta VB plus VD, where VD is the voltage across the diode, and that is the 0.7 voltage for the semiconductor diode. So VB equal to eta VB plus VD. Next one, the characteristics of UJT or VI characteristics of the UJT. And this characteristics show the relation between emitter voltage versus emitter current of the UJT. So in this graph of the VI characteristic of UJT, there is the three regions. First one is cutoff region, second one is the negative resistance region, and third one is the saturation region. So there is a peak point where peak point the voltage is Vp, and with respect to this voltage current is Ip, and second point is here in this graph is valley point. At the valley point the voltage is Vb and current is Iv at the valley point, and valley point after the valley point the voltage increase with the current, and after the peak point voltage uh, decrease as current increase. So this is the negative resistance region in which voltage decrease when current increase. So this is the characteristics of the UJT. And now next one is the programmable unijunction transistor PUT. Although it has the same name as UJT, the programmable unijunction transistor structure is not the same. It is actually more similar to an SCR or silicon control rectifier. So basic structure or construction of the PUT, there is 4 layer total, P layer, N layer, P layer, N layer, and 3 terminal. One is anode, second is cathode, and third one is gate. So the symbol of this put transistor as shown in this second figure here. The PUT can be programmed to turn on at a certain voltage by an external voltage divider. This yields a curve similar to a UJT. So this is the circuit diagram of PUT, in which we applied input voltage across the anode and cathode, and also the gate connected two resistance R2 and R3, and by the DC supply voltage V. The graph of this PUT between voltage versus current is similar to the characteristics of VI of UJT. In this graph, also a negative resistance region and saturation region and cutoff region also here. So external resistors R1 and R2 replace uni-junction transistor internal resistor RV1 and RV2 respectively. These resistors allow the calculation of the intrinsic standoff ratio eta. So eta is the standoff ratio here. So first symbol is the unijunction symbols. Second circuit diagram is the PUT equivalent circuit diagram. And here the RBBO equal to R1 plus R2 from the PUT equivalent circuit diagram, and eta intrinsic standoff ratio eta equal to R1 upon R1 plus R2, and BS source voltage equal to eta VB B, and peak voltage equal to VT plus VS. So RG equal to gate resistance equal to R1 into R2 upon R1 plus R2. So these are the some formulas for the PUT parameters. VRA voltage divider R1 and R2 can be specified. BC is the capacitor voltage. So when BC is greater than VR, the put will conduct. So this is the condition for the conduction of put in that case when VC is greater than VR. Now UJT as a basic UJT relaxation oscillators. So this circuit diagram shows the UJT relaxation oscillator circuit diagram by use of UJT transistor. Here assume in this circuit that the initial capacitor voltage BC is 0 when the supply voltage VBB is first applied. The UJT is on the off state. I is 0 and C charges exponentially through the R1 toward VBB, and we can also see that process in this circuit diagram. When the supply voltage VC equal to VE emitter voltage reaches the firing potential BP, the UJT first and C capacitor discharge exponentially through R2 until VE emitter voltage reaches the valley potential VB, valley voltage. So when VE reaches the valley potential VV, the UJT turn off and IE emitter current goes to 0 and the capacitor is recharged. This process repeats itself to produce the waveform for BC and BR2 as shown below. This is the waveform for the capacitor voltage in which the capacitor is charged for the time t equal to R1 C1 and maximum charge up to voltage BP, and start from this capacitor VV. So minimum voltage equal to value voltage and maximum voltage of the charging capacitor is the peak voltage. So this is the charging time is the R1C and discharging time is the T equal to RV1 plus R2 into C. So this is the charging and discharging time waveform of the capacitor in UJT. This waveform for the VR2. So here this is graphical representation between VR2 versus time. So here the time duration is waveform of VR2 is T equal to RV1 plus R2 into C. And this waveform also show the UJT charging and discharging, and for the VCE versus T and VR2 versus T. So these are the two waveforms for the UJT as a relaxation oscillator. Condition for switching on. To switch on a UJT, the emitter current IE must be able to reach the peak current IP, that is the peak current IP. So here BR1 at the IE equal to IP is greater than IP R1, and condition for switching on. So in this graph of VI characteristics of UJT, there is the three regions: cutoff region, negative resistance region, and saturation region. So here VE saturate is greater than to the VB voltage or valley on voltage, and here the IV is the valley current and VB is the valley voltage. So VP is the peak point voltage for the UJT in switching on modes. So in other words, R1 must be small enough such that emitter current is not limited to a value less than peak current when VC equal to VP or charging voltage equal to peak voltage. So this is the condition for the switching on of UJT relaxation oscillators. Now from this circuit diagram, the VB voltage greater than IP R1 plus VP and VB minus VP is greater than IP R1 and also R1 is less than VB minus VP upon IP. So this is the value of resistance R1 of this circuit's diagram. And next is the condition for the switching off for the UJT relaxation oscillators. To switch off a UJT, the emitter current IE must drop below IV valley current when VC equal to VB or charging voltage equal to valley voltage. Hence, from this circuit, the voltage across the base VBB is less than IVR1 plus VBB, and also VBB minus VB less than IVR1, and R1 is greater than VB minus VB upon IV. So this is the R1 value for the off state. So thus to ensure the switching on and off, the following conditions must be met. So from the this waveforms, we can calculate the time t1 and time t2. So t1 time equal to R1 C natural log of VBB minus VB upon VBB minus VB, and time t2 equal to RB1 plus R2 into C natural log of VB upon VB. So this is the value of time t1 and time t2. The periodic time t equal to t1 plus t2. In many cases T1 is very large as T2. Therefore, in this case, T approximate equal to T1 and equal to R1C natural log of base voltage minus valley voltage upon base voltage minus peak voltage. So this is the time T in that case when T1 is very greater than T2. Therefore, when base voltage and peak voltage are much greater than BB1, then T equal to R1C natural log of base voltage upon base voltage minus peak voltage. And if eta base voltage is very large as compared to BP, and BP approximate equal to eta into base voltage, in that case T equal to R1C natural log of base voltage upon base voltage minus eta base voltage. So T equal to R1C natural log of 1 upon 1 minus eta. The frequency will be F equal to 1 upon T. So F equal to 1 upon R1C natural log of 1 upon 1 minus eta. So now we compare the UJT by the bipolar junction transistor. So bipolar junction transistor also have the two junctions and also three terminal device, and also three layer semiconductors. Device consists of either N or P type layers of material, of 2P and 1N type layers of materials. So There is two types of BJT. First one is PNP transistor and second one is the NPN transistor. So BJT in each transistor, following points to be noted. There are two junctions. What in UJT one junction. So transistor can be considered as two diodes connected back to back. What in UJT only one junction is exists there, and we have as a diode because diode have the one junction and two layers. One is the N layers and second is the P layers. So in transistor there are three terminals, and also in UJT three terminals uh, device. So in BJT three terminals are anode, cathode, emitter, base and collector. But in UJT three terminals are base 1, base 2 and emitter. So in BJT the middle section is thin than other. So transistor has three sections of semiconductor. The section one side is called emitter and the opposite side is called collectors. So middle section is called base here. So this is the symbol of the transistor which have the three terminals base, emitter and collectors. And terminal emitter, the section of one side that supplies carriers is called emitters. And emitter is always forward wise with respect to base, so it can supply carriers. For NPN transistor, emitter supply volts to its junction. For PNP transistor, emitter supply electrons to its junctions. Next one is the collector. The section on the other side that collect carriers is called collectors. The collector is always reverse bias with respect to base. So for NPN transistor, collector receives holes to its junction, and for PNP transistor, collector receives electrons to its junctions. Next terminal is the base. The middle section which hold two PN junction between emitter and collector is base region, that is the base part. And transistor has three regions named emitter, base and collectors. The base is much thinner than other region. Emitter is heavily doped so it can inject large amount of carriers into the base. Base is lightly doped so it can pass most of the carrier to the collectors. Collector is moderately doped. So the junction between emitter and base is called emitter-base junction, emitter diode. And junction between base and collector is called collector-base junction, collector diode. The emitter diode is always forward bias and collector diode is always reverse bias. The resistance of emitter diode is very small and resistance of the collector diode is very high in reverse biasing case. So working of NPN transistor. From figure, this figure shows the working of NPN transistors. Forward bias is applied here to emitter base junction and reverse bias is applied to collector base junction in this diagram. The forward bias in the emitter base junction causes electrons to move toward base. This constitutes emitter current IE. And as these electrons flow toward emitter base, they try to recombine with holes. As base is lightly doped, only few electrons recombine with holes within the base. These recombined electrons constitute small base current. The remainder electrons crosses base and constitute collector current. So collector current and base current and emitter current. So IE emitter current is the sum of the base current plus collector current. So IE equal to IB plus IC. And for the PNP transistor working, in this circuit diagram, forward bias is applied to emitter base junction and reverse bias is applied to the collector base junction. The forward bias in the emitter base junction causes holes to move toward base. This constitutes emitter current IE. So working of PNP transistor, as this hole flow toward n-type base, they try to recombine with electrons. As base is lightly doped, only few holes recombine with electrons within the base. These recombined holes constitute small base current. The remainder holes crosses base and constitute collector current IC. So these are the symbols for the transistor. First symbol is for the NPN transistor and second symbol show for the PNP transistors. Next, transistor operating modes. So first one is the active mode. In active mode, base emitter junction is forward bias and base collector junction is reverse bias in the active mode. Second is the saturation mode. In saturation mode, base emitter junction is forward and base collector junction is reverse. Sorry, base collector junction is also forward in saturation mode. So in saturation mode, both junction J1 and J2 is forward bias. Next one is the cutoff mode. So in cutoff mode, both junction J1 and J2 are reverse bias, or base emitter junction and base collector junction, both junction are reverse bias. So these are the transistor operating modes: active mode, saturation mode, and cutoff modes. Next one is the transistor connections. So transistor can be connected in a circuit in following three ways. First one is common base, and second one is the common emitter configuration. Third one is the common collector configuration. So there are total three transistor configuration: common base, common collector, and common emitters. This figure shows the common base NPN configuration, and second figure shows the common base PNP configuration. So in common base connection, the common base terminology is derived from the fact that the base is common to both input and output side of the configuration. In common base connections, there is a current amplification factor. So what is the current amplification factor alpha? So alpha is the ratio of change in collector current to the change in emitter current at constant collector to base voltage is known as current amplification factor alpha. So in the formula alpha equal to change in collector current to change in emitter current at constant BCB. Practical value of current amplification factor alpha is less than unity, but in the range of 0.9 to 0.99. So this is the practical value of the alpha. Total emitter current does not reach the collector terminals because a small portion of its constitute base current IB. So IE equal to IC plus IB. Also collector diode is reverse bias. So very low minority carriers passes the collector base junction, which actually constitute leakage current ICBO, which is the leakage current or which is very minor currents in the range of nanoampere or microamperes. So collector current constitute a portion of emitter current alpha IE and leakage current ICBO. So expression for the collector current IC equal to alpha IC plus IB plus ICBO, and also simplify this equation IC into 1 minus alpha equal to alpha IB plus ICBO, and from this equation we have IC equal to alpha upon 1 minus alpha into IB plus ICBO upon 1 minus alpha. So this is the expression for collector current IC. Next one is the characteristics of common base configuration. So first one is the input characteristics. Input characteristics of common base means graph between IE versus BBE or emitter current versus base to emitter voltage. So in this graph, we see here BB versus IE characteristics is called input characteristics. IE increase rapidly with BBE base to emitter voltage. It means input resistance is very small. So emitter current almost independent of the collector to base voltage. Next one is the output characteristics of the common base configuration. That is the between output current IC versus output voltage VCB. So VCB versus IC characteristics is called output characteristics of the common base configuration. Here IC varies linearly with base to collector voltage only when base to collector voltage is very small. As base to collector voltage increase, so collector current becomes constant in output characteristics of the common base. So what is the input and output resistance of the common base configuration? So input resistance, the ratio of change in emitter base voltage to change in emitter current is called input resistance. So Ri equal to change in base to emitter voltage to change in emitter current. And next one is the output resistance. So output resistance is the ratio of change in collector base voltage to change in collector current is called output resistance. So R naught equal to change in base to collector voltage to change in collector current. So that is the input and output resistance of the common base configurations. Next configuration or next common emitter connections. The common emitter terminology is derived from the fact that the emitter is common to both the input and output side of the configurations. So in these two circuit diagrams, the first figure show common emitter for NPN configuration and second figure show common emitter PNP configuration. Here, so base current amplification factor beta in common emitter connections. In common emitter connections, input current is base current and output current is the collector current. So ratio of change in collector current to change in base current is known as base current amplification factor beta. So beta equal to change in collector current to change in base current. This is the base current amplification factor beta. Normally, only 5% of emitter current flow to base. So amplification factor is greater than 20. And usually this range varies from 20 to 500 of the beta. So what is the relation between alpha and beta? So we can find out the relation between beta and alpha. So we know that beta equal to del IC upon del V and also alpha equal to del IC upon del IE. And also we know that IE equal to IB plus IC. Take the del of both sides of this equation. So del IB equal to del IE minus del IC. And so put the value of del IB in the equation of beta. So beta equal to del IC upon del IE minus del IC. And also divide the denominator and numerator by the del IE. So beta equal to del IC upon del IE upon del IE upon del IE minus del IC upon del IE. So this will be equal to alpha upon 1 minus alpha. So beta equal to alpha upon 1 minus alpha. So this is the relation between alpha and beta for the transistors. Next one is the expression for the collector current and emitter current. So we know that IC equal to alpha IE plus ICBO, and also we have IE equal to IB plus IC. Put the value of IC in this equation, so we have IE equal to IB plus alpha IE plus ICBO, and simplify this equation and we find out the value of IE equal to IB upon 1 minus alpha plus ICBO upon 1 minus alpha. So I equal to 1 plus beta into IB plus 1 plus beta IC. So these are the two reference books for this topic. First one is the Electronics Device and Circuit by Millman and Halkias. Second one is the Fundamental of Electronics by Bell. And there are some multi-choice questions. And now we will discuss the multi-choice questions. So question first is, in a transistor highly doped part is option A emitter, option B base, option C collector, option D none of the above. So here correct answer option A. Transistor is highly doped part is emitter. In next question, in a transistor with normal bias, option A, the emitter junction offers high resistance. Option B, the emitter junction reverse bias. Option C, the emitter junction has a low resistance. Option D, none of the above. So in a transistor with normal bias, the emitter junction has a low resistance. So here correct answer is option C. In next questions, in a BJT, a base region is sandwiched between emitter and collector. Option B, the collector is sandwiched between base and emitter. Option C, the emitter region is sandwiched between base and collector. D is none of the above. So in a BJT, the correct answer is option A. The base region is sandwiched between emitter and collectors. And next, amplifier are oscillators using BJT operate in option A inverted mode, option B active mode, option C cutoff mode, and option D saturation mode. So here correct answer is option B in active mode. In a BJT, as a collector to base voltage increase, the emitter current A remains same. Option B increase slightly. Option B increase slightly. Option C decrease slightly. Option D depend upon doping of the emitter region. So here correct answer is option B increase slightly. So thank you. Thank you very much.